In 9.7 we're going to look at Taylor polynomials and approximations that we can make for functions. The idea that people had was that we can use polynomials to approximate other functions. In other words, some function p of x, a polynomial, approximates f of x for some value. And we're going to start with our polynomial equaling the function at c, and that means that our polynomial will be centered at that c value. A linear graph through c would approximate the function if it had the same slope. That is, the derivative of both of them would be equal at c. We want to find a first degree or linear approximation of e to the x. To do this, we want to find the derivative of f of x. Well, that's just e to the x. And then I want to evaluate the function and the derivative at 0. And both of those happen to be 1. If I'm saying that the function is equal to my polynomial at c, I'm saying that this is going to equal a sub 0 plus a sub 1 times 0. My function, e to the x, has to equal the polynomial when they're both evaluated at 0. Therefore, a sub 0, the y-intercept of this line, would have to be equal to 1. The derivative of p is equal to a sub 1. So my derivative evaluated at 0 of the function and the derivative of my polynomial evaluated at 0 have to be equal. And I now know that a first degree approximation for e to the x is 1 plus x. If we graph these two things, 1 plus x will be tangent to e to the x at x equals 0. Or at least they'll intersect. But as we move away from this value of c, away from 0, our line gets farther and farther away from our curve. To give our approximation a little bit of curvature, we can add a quadratic term to give us a better approximation. So now we're going to say that the second derivative of each of these is equal to each other evaluated at c. So the second derivative of function f is e to the x still. So f prime of x evaluated at 0, f double prime is equal to 1 still. So my second polynomial will be 1 plus x, that's the linear piece, plus a constant times x squared. Well, that evaluated at 0 the derivative evaluated at 0, if I take the second derivative of my polynomial, I end up with 2 times a sub 2 and that has to equal 1. The first derivative of my polynomial would be 1 plus 2a sub 2x. My second derivative would just be 2 times a sub 2. Evaluate that at 0, that has to equal the function evaluated at 0. So a sub 2 is 1/2 x. So my second degree polynomial that approximates e to the x is 1 plus x plus 1/2 x squared. And I could continue to find derivatives and set them equal like I've done it for the first degree and the quadratic. But in general, a polynomial that approximates e to the x, an nth degree polynomial, will be 1 plus x, that's our linear part, plus x squared over 2, plus x cubed over 3 factorial, plus so on and so on, plus x to the n over n factorial. That is approximately e to the x. And the more terms we add on, the better the approximation is going to be, provided that we're centered at 0. A definition here for a Taylor polynomial and a Maclaurin polynomial. One at a time. If function f has n derivatives at any c value, our nth degree polynomial is found by taking the function evaluated at c plus the derivative evaluated at c times x minus c plus the second derivative at c over 2 times x minus c squared plus the third derivative at c over 3 factorial times x minus c cubed plus yada yada yada. And if I go back to this e to the x, this is actually centered at 0, not at c. And that's a Maclaurin polynomial. The function evaluated at 0, well, e to the 0 is just 1, plus the first derivative evaluated at 0, well, that's also 1 times x, plus the second derivative at 0 over 2 times x squared, plus the third derivative at 0. Well, the third derivative at 0 would be e to the x. E to the 0 is 1. So 1 over 3 factorial times x cubed plus yada 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 like that. Note the similarities here. All I'm doing is I'm putting zeros in for all of these values of c in the generic Taylor polynomial. So I want to find p sub 0 through p sub 4 and finally p sub n for f of x equals the natural log of x centered at 1. To do this, we're going to need a bunch of derivatives. And I'm going to need to evaluate each of those at 1. The natural log of 1 is 0. The derivative of x is 1 over x. Evaluated at 1, we get 1. Second derivative of f, negative x to the negative 2. That derivative evaluated at 1 is going to be negative 1. The third derivative of x will be 2 over x cubed. Evaluated at 1 being 2. The fourth derivative of x, negative 6 over x to the fourth, and evaluated at 1, we get negative 6. In general, the nth derivative is given by an alternating term, negative 1 to the nth times n minus 1 factorial over x to the n. I can now write my polynomials. My 0-degree polynomial is just equal to 0. My 1st-degree polynomial would be 0 plus 1 times x minus 1. This would be f prime of 1 and then x minus the c value. In other words, just x minus 1. The 2nd-degree polynomial would be that x minus 1 plus negative 1 over 2 times x minus 1 squared. The 3rd degree, I take the 2nd degree and I'm going to add on the 3rd derivative evaluated at 1 over 3 factorial, so that would be 2 over 6, which is 1/3, times x minus 1 cubed. My 4th degree Taylor polynomial, x minus 1 minus 1/2 times x minus 1 squared plus 1/3 times x minus 1 cubed, and then minus 6 over 4 factorial, 6 over 24, which is 1/4, so in general, my nth degree Taylor polynomial would be x minus 1 minus 1 over 2 times x minus 1 squared plus 1 over 3 times x minus 1 cubed minus 1 over 4 times x minus 1 to the 4th plus yada 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 plus 1 over n plus negative 1 to the n minus 1 or n plus 1, because I want the even terms to be negative, over n times x minus 1 to the n. All I'm doing is I'm plugging these values I get into this Taylor polynomial, which you can find in your formula packet. Now I want to find the Maclaurin polynomials 0, 2, 4, and 6 for cosine of x, and then I want to use the 6th Maclaurin polynomial to approximate the cosine of 0.1. So I'm going to need to find derivatives. Second derivative would be negative cosine x. Third derivative is sine x. Fourth derivative is cosine x. The fifth derivative is, I'm now repeating what's going on, so this is equal to negative sine x. And the sixth derivative would be negative cosine x. And because this is a Maclaurin polynomial, I'm evaluating these at 0. So the cosine of 0 is equal to 1. Sine of 0 is 0. Second derivative evaluated at 0 is negative 1. Third derivative at 0 is 0. Fourth derivative is 1. Fifth derivative at 0 is 0. And the sixth derivative at 0 is negative 1. So my 0-degree Maclaurin polynomial is just going to be 1. Note there isn't really a first-degree Maclaurin polynomial for this because we're adding on 0 times x, so that doesn't change. That's why I'm only finding the even-degreed polynomials. So the next one's going to be 1 minus, and this is the second degree. So minus the function evaluated at 0, or the second derivative at 0, over 2 times x squared. The fourth degree will be 1 minus 1/2 x squared. Remember, I'm skipping the third because it's equal to 0. Plus 1 over 4 factorial times x to the fourth. And the sixth degree polynomial is 1 minus 1/2 x squared plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth. And I can use this polynomial to approximate the cosine of 0.1. And in doing this, we find that a substitution gives us 0.995004165. And what you should hopefully recognize is the more terms I add on, the closer this is going to get to a value of 1. And the closer it's going to get to approximating what the cosine of 0.1 really is if you actually plug it into your calculator. Now for the sine function, take note that the derivatives would flip-flop and we'd have the odd terms being equal to 1 and negative 1. So the Maclaurin polynomial for sine would have the odd-powered terms. Here are problems for you to try with this first section, just getting a feel for how Taylor and Maclaurin polynomials work.